So I broke it down into the two internal components, member AD and member DBC. So in the first free body diagram, we have the applied loads. We can't choose anything about those. We have to copy those exactly. We have that roller at A. The roller is a normal force, so we know its direction has to be up. So that's kind of determined for us. We don't know its value, though. And at D, we have that internal pin connection between the two members. So I chose in the first picture to assume dx was right and assume dy was up. Again, it's fine if you assume dy was down or up or dx was right or left. As long as you're consistent in your pictures, then that's the important feature. So that was the first free body diagram, which is linked to the second free body diagram. At D, we have that same pin connection, but again, it's an internal force. So I made the assumption already right and up for dx, dy. So I'm obligated to assume left for dx, down for dy, for that internal connection between the two members. So so I have to model it that way based on my picture 1. I have another roller at B, so I know that has to push up. I have that applied couple, I have that applied load. And then at C, I have that external pin support, so I can choose the directions I want to assume. So I chose, just for simplicity, CX right and CY up. So between the two pictures here, I have 3 unknowns, 4 unknowns, 5, 6 total unknowns, and 2 rigid body, free body diagrams. So I should be able to get the 6 equations I need to solve for the 6 unknowns in this system. All right, so based on these, I did sum of forces x, y, which those are just always what we're going to use. And like I was just saying, I did choose to take the moment about D in my first picture. Here, because in the first picture there are only 3 unknowns, it's not going to matter because here I have 3 equations for 3 unknowns, so it will be solvable. In picture number 2, though, this is where now I have 4 unknowns. So now in that picture, I did take this moment around C. To kind of follow my own rule of thumb, I probably should have done A here. But in this case, like I said, it turns out not to matter. Because now if I look, I can go now equation 1, and I can start to get some solutions out of this because there are only 3 unknowns in the first picture. So based on equation 1, I can get that dx is 2 kip. And here I'm using exact values for the sine and cosine. That's where the 1/2 and the √3/2 are coming from. And using equation 3, I can find ay is going to be 9.59 kip. That's an external force, so I can say that's up. I can feed that into equation 2 to find dy is 1.87 kip. The dx, dy are the internal forces here. This, again, was just, I arbitrarily said it was right in this picture, therefore left in this one, up in this picture, therefore down in this picture. Had I assumed this was left and this was down, that's perfectly fine as long as I make the opposite assumption in here. But what's going to come out is that we've gotten a negative dx value and a negative dy value, which again is fine as long as it matches what my assumptions were in the picture. So if your signs are different, as long as you can interpret it, that's what's going to matter. If I go then to equation 4, now that I know the value of dx, I can get the value of cx, that external force, is 9.2 kip. Oops. So that is actually indeed to the right. If I go to equation 6 next, I know dy, so I can find by, which is the roller, is 8.54 kip, which is up, and the roller has to be up, or A has to be up, dy has to be up. So those are kind of quick checks here initially, since the rollers can only push. Cx could be left or right. It turned out that it's to the right. And finally, if I come back to equation 5, now that I know by and now that I know dy, I can find cy is 2.93 kip, and that will be up.